What if the biggest thing you've ever imagined isn't even close? What if there are structures in space so vast that a beam of light could spend most of cosmic history just trying to cross them? Not a galaxy, not a cluster of galaxies, something far larger. Today, we're stepping back, again and again, climbing the scale of the universe itself. From our local cosmic address to structures so enormous they make scientists argue about whether the universe is even supposed to allow them. Let's start where we live. This is Laniakea, our galaxy. The Milky Way, with hundreds of billions of stars, is just a single grain inside it. Laniakea is not a solid object. It's a vast region where thousands of galaxies are slowly drifting along invisible gravitational currents. Picture leaves floating on a river, different streams, different speeds, all moving toward the same destination. That destination is a deep gravitational pull known as the Great Attractor. From one edge to the other, Laniakea spans more than 500 million light years. Light itself would need 500 million years to make the journey. And this is only the beginning. Now we zoom out again. In 2024, astronomers uncovered something unexpected. A structure hiding in plain sight. They called it Kipu after ancient knotted cords used to store information. The name is fitting, because what they found was not a blob, but a branching cosmic network. Using X-ray observations, scientists trace enormous chains of galaxy clusters stretching across over 1 billion light years. Not dense, not obvious, so faint and spread out that it took decades of better instruments to notice. Kipu isn't far away in cosmic terms. It sits in our local universe, which raises a disturbing possibility. Structures this large can bend light, distort distance measurements, and subtly influence how we calculate the expansion of the universe itself. Meaning Kipu may have been quietly shaping our data long before we knew it existed. But now we reach the structure that made astronomers uneasy. In the early 2000s, a massive sky survey revealed something flat, long, and difficult to explain. A continuous wall of galaxies, the Sloan Great Wall, spanning nearly 1.4 billion light years. It wasn't supposed to be there. Cosmology relies on a simple assumption. Zoom out far enough, and matter should be evenly spread. No giant clumps, no cosmic continents. Yet here was a structure pushing against the maximum size theory said was reasonable. It didn't break the rules, but it bent them. Then came something even stranger. In 2013, researchers noticed an unusual grouping of quasars, the blazing hearts of ancient galaxies powered by supermassive black holes. 73 of them, separated by unimaginable distances, yet appearing linked across 4 billion light years. They called it the Huge Large Quasar Group. And yes, that's really its name. If it's a true structure, it exceeds the expected cosmic size limit by several times. But here's the problem. Quasars are rare, and deciding what counts as connected depends heavily on statistics. Some scientists argue we're seeing a pattern because the human brain is excellent at finding them, even where none exist. So is it real? No one fully agrees. And that takes us to the final contender, possibly the largest structure ever proposed in the observable universe. The Hercules Corona Borealis Great Wall. Its estimated size is staggering, up to 10 billion light years across. That's a significant fraction of the entire observable cosmos. This structure wasn't found with galaxies or clusters, but through gamma-ray bursts, the most powerful explosions known. Astronomers noticed that these bursts weren't randomly distributed. Too many appeared in the same distant region of space. The odds suggested something enormous might be there, but the data is thin. Gamma-ray bursts are rare, and small samples can mislead. So this structure sits on the edge between discovery and illusion. If it's real, it challenges the idea that the universe smooths out at large scales. If it's not, It reminds us how careful science must be when staring into the deepest distances. So what we learned? We live in a universe that builds on a scale almost too large to comprehend. From flowing superclusters to branching cosmic webs, to walls that stretch across billions of light years. Each new survey, each sharper telescope, forces us to rethink what we thought the universe should look like. And maybe that's the point. Because every time the universe surprises us, it's not failing the rules. It's inviting us to write better ones. So let me ask you, if the largest of these structures are real, does the cosmological principle still hold? Or is there something fundamental about gravity, matter, and time we've yet to uncover? Tell me what you think. And if you're ready to go deeper, dark matter might be the invisible framework holding all of this together. I'll see you there. So how does the universe even make structures as big? To answer that, we have to rewind almost to the beginning of time. After the Big Bang, the universe wasn't smooth. It was slightly uneven, tiny ripples in density, barely 1 part in 100,000. But gravity doesn't need much. Where matter was just a little denser, gravity pulled harder, and over billions of years, those tiny differences grew. Dark matter did most of the work. Unlike normal matter, dark matter doesn't collide, doesn't emit light, and doesn't slow down. It flows freely through space, forming vast invisible highways long before galaxies ever existed. Ordinary matter followed those paths. Gas streamed along dark matter filaments, piling up at intersections, igniting stars, forming galaxies, then clusters. This is why the universe looks the way it does today. Not random, not uniform, but shaped like a cosmic web. Filaments, voids, nodes. On small scales, this picture works beautifully. Simulations match what we observe. Galaxy surveys line up with theory. But then we keep zooming out, and the web keeps going. At some point, the structures appear larger than the rules say they should be. That's where the tension begins. The cosmological principle was never meant to describe neighborhoods. It was meant to describe the universe as a whole. Zoom out far enough, and everything should average out. No direction should be special. No place should be privileged. Yet structures like massive walls and quasar groups blur that line. They don't completely violate the principle, but they sit uncomfortably close to its edge. Some cosmologists argue we're misinterpreting what structure really means. A wall of galaxies is not a solid object. It's a statistical overdensity, regions where matter is slightly more concentrated than average. If you zoom out even further, those differences may still smooth away. Others disagree. They point out that the largest claimed structures approach the size of the observable universe itself. At that scale, there may not be a larger reference frame to average over, which raises a deeper question. What if the universe never truly becomes smooth? What if homogeneity is only approximate, a useful assumption, but not a perfect truth? This wouldn't break cosmology, but it would reshape it. Some models already allow for this. Inflation theory suggests the universe could contain rare, enormous fluctuations spread across vast distances. Most regions look average. A few don't. And those few are the ones we're starting to notice. There's also the role of cosmic time. We're observing these structures at different ages of the universe. Some walls and quasar groups exist only briefly on cosmic timescales. Given enough time, they may stretch, thin, and dissolve back into the background. What we're seeing could be a snapshot, not a permanent feature. And then there's observation bias. We map the universe from a single point in space. Our surveys have edges. Our instruments have limits. Our samples are incomplete. Patterns can emerge simply because of how we look. This is especially true for structures detected through rare events like gamma-ray bursts, which is why the largest claimed structures remain controversial. And that controversy is healthy. Because science doesn't advance when ideas are comfortable. It advances when data pushes theory into uncomfortable corners. Right now, we're in one of those moments. New telescopes are coming online. The Euclid mission, the Vera Rubin Observatory, next-generation skies surveys mapping billions of galaxies in 3 dimensions. For the first time, we'll be able to test whether these megastructures are real features of the universe or statistical mirages. Either answer would be profound. If they're illusions, it tells us how careful we must be when interpreting cosmic patterns. If they're real, it means the universe is capable of organization on scales we never expected. And that changes how we think about gravity, dark matter, and the origin of structure itself. The biggest lesson may be this. The universe doesn't owe us simplicity. It builds with subtle rules, applied over immense time, across distances so large they break intuition. And every time we think we've reached the edge of understanding, the universe quietly adds another rung to the ladder. We climb, we adjust, we keep looking. Because out there, on the largest scales imaginable, the universe is still teaching us how it works.